Hi, welcome to Sunil Maths tutorial. From today onwards, we start a new lecture series on Galois theory, which is also known as field theory. In this chapter, we learn four chapters: algebraic extension of fields, normal and separable extensions, Galois theory, and applications of Galois theory to classical problems. Let us see the topics. In the first unit, we are going to cover irreducible polynomials and Einstein criterion, adjunction of roots, algebraic extensions of fields, algebraically closed fields. In the second unit, normal and separable extensions, we cover splitting fields, normal extensions, multiple roots, finite fields, and separable extensions. In the third unit, Galois theory, we learn about automorphism groups and fixed fields, fundamental theorem of Galois theory, and fundamental theorem of algebra. In the last chapter, applications of Galois theory to classical problems, we learn five topics: roots of unity and cyclotomic polynomials, cyclic extensions, polynomials solvable by radicals, symmetric functions, ruler and compass constructions. So to cover all these four units, I am going to use the textbook Abstract Algebra written by Bhattacharya, Jain and Nagpal. Let us start with Introduction, Chapter 1, Algebraic Extension of Fields. The very first topic is irreducible polynomials and Einstein criterion. First, let us see the definition of polynomial. Let us see the definition of polynomial. If small n is a positive integer and a0, a1, a2 and so on, an are real or complex numbers where an not equals to 0, then the expression of this form f of x is equals to a0 plus a1x plus a2x square plus and so on plus an x power n is called a polynomial in the variable x of degree n. So polynomial means an expression of the form f of x is equals to a0 plus a1x plus a2x square plus and so on plus an x power n, where remember that an is not equals to 0. An expression of this form is called a polynomial. This is known as polynomial. In the variable x of degree n, here a0, a1, a2 and so on an are either real or complex numbers. These a0, a1, a2 and so on an are called coefficients of the polynomial f of x. Here the last term the initial term a0 is called constant term or independent of x term. Constant term or independent of x term, and an is called leading coefficient. This an must be not equals to 0 because an must be not equals to 0. If an is equals to 0, then the degree of the polynomial differs. So remember that. And also you remember that here we said that the degree of the polynomial is n. It means that n must be a positive integer. So this is the definition of polynomial. Polynomial means it is an expression which is clearly in this form: f of x is equals to a0 plus a1x plus a2x square plus and so on an x power n, where an not equals to 0, is called a polynomial in the variable x of degree n. Here a0, a1, a2 and so on an, they are either real or complex numbers and they are called coefficients of the polynomial f of x, and a naught is called constant term or independent of x term, and this an is called leading coefficient. Remember that an must be not equals to 0. If it is equivalent to 0, then the degree must be less than n, and n belongs to z plus. It means n is always a positive integer. So right, let us see the next definition, which is known as constant polynomial. Constant polynomial. A polynomial f of x is said to be constant polynomial if all the coefficients a1, a2 and so on an must be equivalent to 0, but a not equals to 0. What it means? Then the expression f of x must be in this form. F of x is equals to a naught. F of x is equals to a naught, where a naught is not equals to 0, all the other coefficients a1, a2 and so on an is equals to 0. Then the polynomial is known as constant polynomial. Let us see the next definition, zero polynomial. Zero polynomial means here all the coefficients are 0. Simply you know that it can be written as f of x is equals to 0. Here, the degree of the polynomial, zero polynomial, cannot be defined. If all the coefficients a0, a1, a2 and so on an is equals to 0, then simply f of x is 0. So, here the degree of the zero polynomial cannot be defined. Now, let us see the next definition, polynomial ring. Let us see the definition, polynomial ring. Here it is, polynomial ring. Let capital R be a ring, then the set of all polynomials R of x forms a ring with respect to addition and multiplication defined as follows. F plus g is equals to a naught plus b naught, comma a1 plus b1 and so on. Fg is equals to e naught e1 and so on en, where en is equals to a naught bn plus a1 bn minus 1 plus and so on, where f of x and g of x are polynomials defined over capital R of x. Then R of x is called polynomial ring or ring of polynomials in capital X. So let us explain that. Capital R be a ring. Capital R be a ring. Everybody knows the definition of ring. Ring means this capital R is a non-empty set together with two binary operations, addition and multiplication. Together with two binary operations, addition and multiplication, is said to be a ring if it satisfies three properties. The first property is capital R with respect to 2 plus is an abelian group, and capital R with respect to multiplication is a semi group, and distributive laws holds in capital R. Distributive laws holds in capital R. So ring means it is a non-empty set together with two operations addition and multiplication satisfying three properties. It is an abelian group under addition, semi group under multiplication, and distributive laws holds in capital R. Now the symbol R of x, capital R of x, represents the set of all polynomials, the set of all polynomials in the variable x. R of x represents the set of all polynomials in the variable x over the ring capital R. Over the ring capital R. So this set forms a ring, or this set forms a ring, or this set satisfies all the properties of a ring with respect to these two operations. F plus g is equals to a naught plus b naught, a1 plus b1, and so on, an plus bn, and fg is equals to e1, e2, and so on, en, where this en is equals to a naught bn plus a1 bn minus 1 plus and so on plus an b naught. Remember that where f is nothing but the polynomial f of x, which is in this form a naught plus a1x plus a2x square plus and so on plus an x power n, where an not equals to 0, and g of x is also polynomial b naught plus b1x plus b2x square plus and so on plus bn x power n, where Bn is also not equals to 0. These both f of x comma g of x are polynomials belongs to capital R of x. With respect to polynomial addition f plus g and polynomial multiplication fg, the set capital R of x forms a ring with respect to these two operations. This ring is known as polynomial ring. This ring is known as polynomial ring. Polynomial ring or ring of polynomials. Ring of polynomials. Remember the symbol R of x. R of x represents the ring of polynomials. Now let us see the point. Suppose let capital F be a field. Let capital F be a field and f of x be the ring of polynomials in capital X over capital F. Then this capital F of x, here you use the symbol capital F of x. Capital F of x here is an integral domain. Capital F of x is an integral domain with unity containing capital F as a subring. So the ring of polynomials over the field capital F must be an integral domain with unity containing capital F means containing the field as a subring. The next definition and one of the very very important definition, irreducible polynomial. Irreducible polynomial. Let us see the definition. A non-constant polynomial f of x belongs to capital F of x is irreducible over capital F or irreducible polynomial in capital F of x if degree of f of x greater than or equals to 1 and f of x cannot be expressed as a product of two non-constant polynomials. A product of it is not possible to express, cannot be expressed as a product of two non-constant polynomials. Let us see any polynomial f of x belongs to capital F of x is said to be irreducible over capital F or in capital F of x if it satisfies two properties. The first one, degree of f of x must be greater than or equals to 1, and the second one, it is not possible to write f of x as product of two non-constant polynomials. This is known as irreducible polynomial. To understand the definition of irreducible polynomial, let us see two examples. Suppose f of x is equals to x square minus 2 defined over capital Q of x, I mean ring of rationals, where capital Q is the field of rational numbers. Remember that, rational numbers. So it is not possible to split here. So f of x is irreducible over Q. And suppose f of x is equals to x square plus 1 defined over capital R of x, where capital R is real numbers. This is also irreducible polynomial. It is not possible to split this polynomial over capital R. But there is an important point to remember. F of x is equals to x square minus 2 can be written like this. X plus root 2 into x minus root 2. But this root 2 is an irrational number. Plus root 2 and minus root 2 are irrational number. So x square minus 2 cannot be split over capital Q. X square minus 2 cannot be split over capital Q because root 2 and minus root 2 are irrational numbers. Similarly, f of x is equals to x square plus 1 can be written as x plus I into x minus I, where that I is imaginary unit, where that I is imaginary unit, that I does not belongs to capital R, that I does not belongs to capital R, that is a complex number. I is an imaginary unit and I square is equals to minus 1. So x square plus 1 cannot be split over capital R, but it can be split in over capital C. So this polynomial irreducible over capital R but reducible over capital C. Irreducible over capital R but reducible over capital C. Reducible over capital C. So remember that reducibility or irreducibility of the polynomials depends upon the nature of the field. Depends upon the nature of the field. So let us see one more example. F of x is equals to x square. F of x is equals to x square plus 2. So here are x square plus 4. I mean one of the simple polynomial. So this polynomial has no roots in capital R. And also you can conclude here this polynomial f of x can not possible to split. It is not possible to split as product of two polynomials, over capital R. So it is irreducible. It has no roots in capital R. It means it is not possible to split as product of two polynomials over capital R. So it is irreducible over capital R. But remember that the same polynomial x square plus 4 can be written as x plus 2i into x minus 2i. It can be split over C. It has two roots, plus 2i and minus 2i. They are complex roots. So the polynomial can be written as product of two non-constant polynomials over capital C. So irreducibility of the polynomial depends upon the nature of the field. So remember that. So this is the definition of irreducibility. So at the same time we see one more definition of irreducibility. F of x is said to be irreducible if degree of f of x greater than or equals to 1, where f of x is equals to g of x into h of x, such that g of x comma h of x belongs to capital F of x, then g of x belongs to capital F or h of x belongs to capital F. It means either g or h must be a constant polynomial. So here is the same example x square minus 2. You observe that this f of x is irreducible over q, but f of x is irreducible over q, but f of x is not irreducible over capital R. Not irreducible means it is reducible over capital R. So reducible polynomial, it is very simple definition. A polynomial which is not irreducible is said to be reducible polynomial. A polynomial is said to be reducible if it is possible to write as a product of two non-constant polynomials. Again, simple definition. Here see the example x square plus 1. So x square plus 1 can be written as x plus I into x minus I. So it is product of two non-constant polynomials over capital C. So you conclude that f of x is irreducible. I mean x square plus 1 is irreducible over capital R but reducible over capital C. So that is the point. Already we said that irreducibility of a polynomial depends upon the nature of the field. And let us see some important properties of the polynomial ring capital F of x, which are very important for our next theorems and definitions. First one, division algorithm holds in f of x. Very important. Division algorithm holds in the polynomial ring f of x. This means that f of x belongs to f of x, capital F of x, and g of x not equals to 0 belongs to f of x. Then there exists two unique polynomials q of x and r of x belongs to capital F of x, satisfying the condition f of x is equals to g of x into q of x plus r of x, where either r of x is equals to 0 or degree of r of x is always less than degree of g of x. Degree of g of x. So division algorithm holds in the polynomial ring. The next second property, capital F of x is a principal ideal domain. Remember that capital F of x is a PID. PID means principal ideal domain. And capital F of x is a unique factorization domain. UFD, unique factorization domain. And the units of capital F of x are non-zero elements of f. And the next one, very very important one, if p of x is irreducible in the polynomial f of x, then f of x by generator p of x is a field, and also the converse is true. Suppose the polynomial p of x is irreducible polynomial, then f of x generated by the polynomial p of x, f of x by generator p of x, f of x by generator p of x, this must be a field. This must be a field, and the converse also true. Whenever f of x by quotient ring, this is known as quotient ring, f of x by generator p of x is a field, then obviously this p of x must be irreducible polynomial. So we go for a theorem. Remember this, all the 5 properties are very important to prove next theorems. Let us see the statement of the theorem. Let f of x belongs to capital F of x be a polynomial of degree greater than 1, and if f of alpha is equals to 0 for some alpha belongs to f, then f of x is reducible over capital F. Let us prove this theorem. They given that f of x is a polynomial. F of x is a polynomial of degree greater than 1, first of all, of degree greater than 1. And then f of alpha is equals to 0 for some alpha belongs to f. So right, they given that capital F of x is a polynomial ring, capital F of x is a polynomial ring, and f of x is a polynomial belongs to capital F of x whose degree is greater than 1. Degree of the polynomial f of x is greater than 1. And also they given that one condition, f of alpha is equals to 0 for some alpha belongs to capital F. F of alpha is equals to 0 means this condition implies as alpha is a root of the polynomial. Alpha is a root of the polynomial f of x. If alpha is a root of the polynomial, then obviously x minus alpha is a factor of the polynomial. X minus alpha is a factor of the polynomial f of x. Now take right, let us see please. F of x is a polynomial defined over capital F of x, and degree of f of x is greater than 1, and they given that f of alpha is equals to 0 for some alpha belongs to f. If f of alpha is equals to 0, then x minus alpha is a factor of f of x, and take g of x is equals to x minus alpha, which belongs to capital F of x, and you remember that degree of g of x is equals to 1. Degree of g of x is equals to 1. Now we have two polynomials, f of x and g of x, both belongs to the polynomial ring capital F of x, and capital F of x satisfies the division algorithm. Capital F of x satisfies the division algorithm. By the division algorithm, there exist two unique polynomials, q of x and r of x, satisfying the condition f of x is equals to g of x into q of x plus r of x, where either r of x is equals to 0 or degree of r of x is less than degree of g of x. So because of division algorithm. Now in this expression f of x is equals to g of x into q of x plus r of x, replace that x by alpha. It means f of alpha is equals to g of alpha, q of alpha plus r of alpha. So by data f of alpha is equals to 0. By data f of alpha is equals to 0. F of alpha 0 means you have to replace here 0. What is g of alpha? You see here, the polynomial g of x is equals to here. G of x is equals to x minus alpha. X minus alpha. Therefore, g of x is equals to x minus alpha. Therefore, g of alpha is equals to alpha minus alpha. You get 0. 0 means g of alpha also 0 into q of alpha plus r of alpha. This condition shows us 0 is equals to r. That is, r of x is equals to 0. R of x is equals to 0. If r of x is equals to 0, then this expression becomes f of x is equals to g of x into q of x. And you remember that degree of f of x is greater than 1 and degree of g of x is equals to 1. So obviously degree of q of x also greater than or equals to 1. Also, without degree, you observe this here. This is nothing but, what is this? Product of two non-constant polynomials. Product of two non-constant polynomials. It means f of x can be written as product of two non-constant polynomials. It means f of x is reducible. That is the statement of our theorem. You see here, let f of x belongs to capital F of x be a polynomial of degree greater than 1. If f of alpha is equals to 0 for some alpha belongs to f, then f of x is reducible over capital F. This completes the proof. Here you observe the degrees. Here f of x is equals to g of x into q of x, and degree of g of x is equals to 1, and the degree of f of x is greater than 1. So degree of f of x is greater than or equals to 2. Then degree of q of x must be greater than or equals to 1. Hence, f of x can be written as the product of two non-constant polynomials. Therefore, f of x is reducible over capital F. This completes the proof of our theorem. In the next video, we learn some definitions and some theorems of this chapter. Keep learning. Wish you all the best.